In this session, we're going to discuss network design. And the network design in automotive is very similar also to network design in aerospace. So it's going to be the same concept. So it's the main driver for network design and the MBSE flow in general is the complexity that is being that we are seeing that is growing very fast to the level where just adding or throwing in more engineers is not going to solve the issue. We would need more automation and more tooling to be involved to be able to tackle the new challenges in the EE architecture domain, EE architecture development. And that is the main driver for the MBSE flow that we started this morning. Specifically for network design challenges, we're seeing some discontinuities between network designers and the other teams inside the organizations. So we're having silos. The network designer or the netcom team is working in a silo. Different than the EE architecture team or the wiring and harness teams and so on. And these gaps or this working in silos is actually imposing a lot of challenges for the network design. So if one of the feature owners would like to add more features, or adding more signals, how that gonna affect your network design and vice versa. If you're changing your network architecture for some reason like bus load, increase in the bus load, or that the current CAN communication is not enough, how that will affect the wiring and harness domain. So why working in a silo is actually lacking the automation or lacking the bridging the gaps between network designers and the other domains is affecting the quality to a great extent. We were able to live with that in the past, but with the complexity and less time to market and all those challenges, we cannot live with those challenges anymore. We need to have a solution for this dilemma. So adding to that, we have new challenges for the network design coming from the new feature that we're seeing. So automated driving or autonomous driving, vehicle-to-vehicle communication, and also the over-the-air updates. Finally, the AVB audio-video bridging. A lot of different applications or features being added to our vehicle that is going to affect the way we're designing our network into the vehicle. So in the past, for decades, we've been only using mainly CAN and LAN in our vehicles, right? Now, with those features, CAN and LAN is not going to be sufficient. We are looking into CAN-FD. We're looking also into Ethernet and also Wi-Fi connectivity, 5G and 4G connectivity. So new challenges are being imposed into our architecture coming from those new features that we need to add to the vehicle. Not only the feature that actually added those challenges, but also new trends in the network design. One of those is the centralized EE architecture. So moving from distributed system into a zonal mode or zonal architecture, having a centralized node that would fulfill a lot of functionality that have been developed in the past using distributed ECUs. That is a new challenge. How we're gonna affect, how that is gonna affect our network design, how we're gonna deal with that into our model. Also having a software, not only message-based or signal-based communication, but moving toward a service-oriented architecture where there is a server and client into our vehicle that would allow a more dynamic behavior to the vehicle than the static behavior that we have today. How we can deal with that into our network design. So most of the tool that we have, either it's Excel sheets that most of the OEM are using to do network design, would fail to handle those challenges. They were okay to handle the CAN communication because it's by definition very simple. It was also okay to be used to handle link communication, but Excel sheet will fail to handle service-oriented communication, Ethernet with the complexity being part of the Ethernet standard, and so on. So those are some new trends that will make the current tool that we're using is going to fail, and we need a new tool that understands model, not only documentation. And also, finally, AutoSAR. If you're capturing your network design in a documentation, not a model, how are you going to feed the downstream tools, right? How are you going to feed an ECU that is being developed using AutoSAR? So you cannot achieve that if you don't have model for your network, automotive network. So those challenges, actually, how those challenges would affect your vehicle development. If you're not able to understand the bus load into your network, you're going to probably waste a lot of resources. And meaning that you may end up putting your maximum load for a certain bus to be 60%. And you're saying that I'm going to design my CAN bus to be 60% maximum load because I don't know what's going to happen at the physical layer during the actual deployment. So doing that, you're actually adding more weight to your vehicle because you're not able to maximize the benefit or the utilization of your communication buses, right? It may end up also that you're only depending on the physical testing, using Cano or Canalizer to do the physical testing for your network. And that's not going to give you the ability to discover the issues early on in the design process. If you're going to wait until you do the physical testing, that's going to be really late in the process. And the cost for that will be huge compared to having the ability to understand the effect of adding signals or the effect of running out of bandwidth early on in the process, so you can take mitigation actions early on in the process, which is usually by definition will be less cost than waiting until the end. And also, if we don't have if you're not working with models, then you're lacking the automation that is usually come with tools that understand models, and this will hinder the productivity and also will definitely affect the ability to have a quality network design. So if you're using the old way for using documentation for your network design, using mainly Excel sheets or PDF or Visio to capture your network design, a lot of questions you will fail to answer, right? We've seen OEMs are failing to answer those. They started to develop some macros in the Excel sheets or the current tools to answer those for CAN, for LAN. And those methods are failing today to answer those questions for more sophisticated architecture when it comes to service-oriented architecture and Ethernet and CAN-FD. What would be the effect on your network design if you added a new signal? If you moved one signal from one ECU to the other ECU, how that's going to affect your bandwidth, right? What about the gateway design? What about the link utilization for the Ethernet? Those are questions you cannot answer. You cannot predict early on in the process if you're working on documents as part of your network design. Moving from working with documents to working with models, this is gonna help you to answer those questions fairly quick in the process. So the main idea is moving from documentation or working with documents to work with network design tool that would allow you to capture your design or network design in a model. And this model, you can query this model, you can integrate this model and calculate a lot of timing parameter for your network, making sure coming out of the tool you have a network design that has been verified using the timing calculus in the tool. So you're pretty much sure early on in the process that this network design would, when you take this network design into a real hardware deployment and testing, you would get much better result early on in your network design process. So, and this is where Capital would be used to bridge the gap. So what we've learned in the morning is from having multiple sources for models, we started to normalize those models into Capital System Architect, where we brought all the different function from different sources into the tool. And some of those are software functions, some of those are hardware functions, and also we capture the signals that is being used to communicate through those functions. So if those functions are distributed into different boxes, different ECUs, those would be a network signals. And then what we've done also, we took those functions, we did the deployment for those functions into our topology, right? So and as Hans mentioned during the morning session, those allocation can be done either manually or automatically. So at that level, we have our vehicle topology, could be our aircraft topology with the component. Those components are basically an ECU, could be assembly. Function being allocated here, signal being routed to carriers. So pathways and carrier are also captured at that level. From here, you can feed different disciplines, can feed the software, as we've seen in the previous presentation, can feed EDS, and finally can feed also network design. And this is gonna give you the automation part that we were talking about and bridging the silos that we described. Then we brought all those into the physical architecture, and we did the allocation, not only for the function, but more importantly for the signals. So we also defined carriers here, network carriers, and we did the allocation for those network signals into the carriers. So, and then we did the generative synthesis using those stuff on the left side, function, which will end up to be a software component, and then the signal and the carrier will be the buses and signal to for the network. So again, we will feed now the network design. So the ECUs are coming from our topology, signals and clusters are coming from the carriers and electrical signals being captured at the system level. So we are able to jumpstart our network design. So we're not gonna start from scratch. We're starting from the point where the EE architecture stopped, right? So the point that the EE architecture tool is feeding software, the same data that went to the software team, the same data that went to the EDS team is the same data source that came or provided data to the network designer. So we're having a coherent database that is feeding all those disciplines. And in here, this is where we will talk today. The Capital Network tool that is taking the output from the system tool, right? And starting the network design, and finally will also provide an AutoSAR output as a medium to the downstream tools. So in here, this is what we're trying to discuss today, the Capital Network tool for network design. As a quick introduction about the tool, the main intent for the tool is to give the user the ability to have a model-based design tool that understands network. It's a domain tool that understands how network design should be. So it allows you to capture all the network artifacts that you need, and also at the same time giving you the ability to do some timing analysis. So you would capture your timing requirement and do analysis based on your current design, making sure that the design that you did is really fulfilling those timing requirements, and giving you the ability to have use some built-in matrices to make sure that yes, you're on the right track for this network design before going to the downstream tools and having the integration between the network and software that we discussed in the previous session. And also having the ability to have a generative design for network. When you talk to a network designers, usually they take, if they have thousands of signals, as we probably know, to pack those thousand signals or tens of thousands of signals into messages, that can take forever, really forever. It's not weeks, it's not months, it can really take forever from network designers. And what we're providing here, and we will show in the demo, that those 10,000 of signal can be in few seconds to few minutes be automatically packed into messages. And so we're going down from forever to few minutes or few seconds based on the scale of your network And all that is not based on anything but a real timing model. So you're capturing your requirement. We're giving you some proposal that you can take and leverage to have your network design fulfilling those requirements. So this circle here is showing exactly what this tool is doing. To the left side, we have mainly the logical architecture. That's something you can capture in the tool, or you can get it from system, like what we've seen if you have the stuff already captured in capital systems, where you packed your, or not packed, where you allocated your function and signaled into the architecture. You can feed that into here. We're gonna give you your starting point, which is ECUs connected to buses or clusters and signal being transmitted and received inside your network. So this is gonna be your starting point. And then you're capturing also your timing requirement. This can be captured inside this tool, Capital Networks, or it can be part of the model that you imported from the system level. So if you have this information already, or this requirement already captured into the system level, we can bring that in. If not, then you can use the tool as a standalone, and you can input those requirements into the tool. Those requirements we will discuss in the next slides is basically taking into consideration the end-to-end delay. So if you have a safety critical signal that needs to arrive from the source to the destination within 100 milliseconds, if it took more than 100 milliseconds, the system may fail, right? Because it's a function, it's a critical to the safety. Then your maximum allowed delay is 100 milliseconds, and this will be your requirement, and you will do your network design, and then we'll compare this result with this requirement and see how much margin do you have, were you able to fulfill this requirement or not, and what we can do to fulfill this requirement if you didn't already. And also the variability. So any OEM has usually what we call it the 150% design. Right? So 150% design, meaning that it's a design that had all the variant and option from which you can drive different car or different vehicle platform, right? So the tool would allow you to capture the model for this 150% design, and then give you the ability to do the network design on a specific platform, and then release those platforms as you go. So this is basically your input, right? Mainly these two, the logical architecture and the timing requirement. And then the tool will do the synthesis for you, meaning that these two information are very enough for the tool to be able to implement or do the frame packing. Get and do all those tens of thousands of signals, do the frame packing, pack those signals into messages based on the timing constraints or requirement that you have captured in the tool. So it would give you a proposal for that frame message, or for that frame packing or message packing, and will give you also some analysis, some timing analysis matrices that actually compare the design that the tool did with the requirement that you provided, given the logical architecture that you also provided. And from here, you have the ability to examine your design to see how good or how bad your bandwidth utilization is, how good or how bad your adherence to the timing requirement that you captured to the left side is. So a lot of, and again, this timing analysis and the synthesis is based on a real accurate timing model. What we've done in the system level when we had these matrices, this was some very basic algorithm to give you the ability to do studies. But here, this is a real timing model for network, taking into consideration the arbitration delay, the worst case latency. And finally, once you're good, once you feel good about your network design based on the analysis reports here, then it's time to go and provide the downstream tools with an AutoSAR format, or maybe a DBC file or a 5x file. Different format can be driven from this model, because it's not documentation. It's not Excel sheet, right? It's a real model that you can after making the analysis on this model, you can provide to the downstream tools. So how the timing model usually works. So we have a sensor usually, and we have actuator, and then we have a processing unit. This processing unit could be a gateway at the same time, and we have also, we have an ECU beside the sensor and another one beside the actuator. So what we capture here in the tool is the end-to-end timing requirement. So meaning that we're keen to capture the publisher delay or the publishing delay, subscribing delay, right? Which is basically since the ECU or the sensor ECU or the actuator ECU is receiving the signal until it's propagating that to the bus, or receiving that from the network bus and starting to process this signal and do the actuation. And we also capturing the communication delay over the bus. So once the signal is on the bus and going to processing unit, this is what we call it, the communication delay. And also we capture the processing delay, which could be a gateway delay or application processing delay. So those are part of the requirement, right? And those something we take as a requirement and we do calculate as well. So we do calculate that based on our timing model, and we compare our calculation with your requirement that you capture in the tool. And this is basically, again, taking into consideration all the network-related facts. So if you're using Ethernet, we need to take care of the queue on the switch. How many switches do you have, and what kind of traffic shaping do you use? We take that into consideration and provide timing calculation based on the worst case scenario, and we're comparing our calculation with the value that you provided, and then we can calculate the end-to-end delay and then compare the end-to-end delay with the requirement that you provided. So this is basically how we do it. The worst case scenario, this is what we usually take into consideration. So to understand why this is really important, assume that in here, that the maximum allowed delay for certain signals based on your understanding to the system is here. So you're saying that this signal cannot be delayed more than this maximum allowed delay. Otherwise, the system will not successfully achieve the functionality or could potentially fail. So this is the maximum allowed delay. And then based on your procedure, you don't have a way to predict this time or calculate it, so you're waiting for the physical testing, right? Most of the OEM are doing that today. So if you're doing that, then most probably this is what you will discover using the Canoe or Canalizer. At the physical testing level, this is what you will get. You will find that your network design on the physical layer, this is what the maximum delay that you're observing, right? So you feel good about your design. The maximum delay that you're observing is still behind the maximum allowed delay, so we're good, right? But this is not the case. If you're calculating your the maximum the worst case delay, it's gonna be in this area. So the actual worst case scenario that you will not be able to observe during the testing is actually here. And that means that there is a data loss between what you're seeing here or observing during the testing and what you actually can get to, right, which is the worst case scenario. And this is what we calculate. We calculate that early on and give you a report that the actual worst case scenario that is happening here is being captured in the tool, and we are comparing this one with this one. What you're gonna get into the physical testing, you are comparing this one with this one, so you're gonna get these data loss. So this is the concept behind the network design tool, which is Capital Networks. And as you can see here from these snapshots from the tool, is giving you the ability also to calculate the bus load. The bus load, for example, here is 98%. No one that I'm aware of, right, can have the courage to design their network to be 98%, right? They would maximally go for 70% because they don't know what's going to happen. But using a tool like this, we have customers who's going to 98%, and they are sure, and we are sure that it's going to work eventually when it comes to the physical layer, right? Because we are designing this 98% based on the worst case scenario, right? So giving you the leverage to be able to reduce the amount of wires, and this is not a joke. This is a real thing, right? So once you have the ability to predict that early on, you can decide that I don't need two Canny channels. One Canny channel can do the job for me, right? And the same to move from CAN to CAN-FD, from CAN-FD to Ethernet. Those decisions are now based on some calculation, based on real numbers, right? So, and this is the real value of having a network design tool that understands model, that understands timing, that has a core implementation for timing calculation, and give you the ability to be very confident when you release your artifact to the downstream tools. So just to wrap up, it's basically what we call it the correctness by design, right? So correctness by design, meaning that you have the ability during your design to make sure that you have a consistent design. You don't have any issue with the PDU layout, which is something you cannot discover easily with the current tool like Excel or Visio or other tools, that you don't know that until you do the physical testing that one signal is being packed in the wrong order. You can visualize that and you can detect that early on, that you don't have any overload or any overwritten signals. So this is correctness by design, meaning that you started with requirement, with topology. We took it from there and we gave you a design that we are sure that it's a good proposal to start working on, instead of starting everything from scratch. And those will drive eventually the quality, reliability, and performance to your suppliers as well. So this is a snapshot. I'm going to go through quick snapshots for the tool to show you some of the features that we have. So here, this is your topology, and this is only for one cluster or one bus. Imagine if you're using, for example, DBC++ editor. This is the maximum you can get, right? Just one file for each network. But if you have a 10 clusters, hundreds of ECUs, right? 5 or 4 gateways. This is where the value will appear, right? When you can visualize all this network, as we will see in the demo, visualize all this network in one tool, in one model, right? Going through the network as you want, tracing signals across those ECUs. So this is part of what you can see on the right side here. This is some model changes, some signal tracing and PDU tracing. Here, what I was describing regarding the timing. So bus utilization is being calculated in the background as you're changing the timing parameter. So as you're changing the periods for one of the frames, you will find the bandwidth is being recalculated as you go. So you have a better feeling on what you need to do and what you shouldn't do, right? And finally here, before going to the demo, once we have your network design ready for downstream tools, we have different ways to generate this output. Could be in RXML, which is the AUTOSAR standard format. Could be in DBC file for CAN buses, LDF for LAN, FiBeX for FlexRay and Ethernet. Different ways to get your model out to the supplier based on how your supplier is set up to implement the ECU development. So as a demo here, so in here I'm going to start from scratch. I'm going to import it. I don't have anything here, right? I don't have any ECUs or anything. I'm importing these data from Capital Systems. So I have already a project in Capital System, and I'm bringing in the data here. So you will see here, this is my starting point, which is, again, jumping start your network design. And what I'm going to do, I'm going to try to trace the signal. So once I select one of the signals, you can see that one is transmitting, one is receiving. There is discontinuity here because there is no gateway. So I'm going to try to design the gateway. So now the tool is automatically detecting the gateway modules, and you can see that now a gateway has been identified, and the full trace for the signal is visualized, can be visualized here. And now I'm gonna do the frame packing. So for those signals, I don't have any frames, and I'm gonna let the tool do the frame packing for me. So in a click, in one click, I've been able to get those frames and all the signals being packed into those frames, and the bus utilization is also calculated here. And you can get the contribution for each ECU, how much of a bus load each ECU is contributing to the total bus load for each bus. So basically, we went through going from the system level, getting the data from the system level, and then going through our design to do the gateway design, and then do the frame packing, message packing, and finally doing the timing analysis. The timing requirement were coming already from the system, so when I imported my topology, I was able also to capture the timing requirement during this process. So one of our customers actually got to know or get to experience these values that I was describing. So what I was describing for a tool that has been in the market for more than a decade, CVT, which is it's a joint venture between Volvo and Geely. They are using the tool, and this was a press release. And what they are seeing, basically, that they were able to cut the network design to 50%. And that was based on what I was describing, the generative flow, to be able to back those tens of thousands of signals in few seconds, and instead of weeks and months and sometimes forever, you cannot do this job. You can get that very quick, and you can get that with timing requirement and timing analysis capability. We're gonna take you to be very confident before going to your supplier, right? And so this was one of the press releases that we have with one of our customers. So just to summarize what we discussed today for the network design, we discussed the challenges that we have in this domain, and what a tool like Capital Network can provide to solve those issues or to bridge this gap. Basically, the correctness by design, which is gonna definitely affect your quality, right? As we've mentioned, you can early on detect overlaps in your frame packing. You can detect any inconsistency in your timing for the signals. You can make sure that you have enough bandwidth or efficient bandwidth uses. So you can bring that. You can get that all from the tool, which is the correctness by construction or by design. The optimization, right? So once you have the ability to capture your design and capture your requirement, you are able to understand where are the areas for that I can optimize in, right? Can I grow? Can I make use of the bus bandwidth that I have, right? Instead of just adding more clusters or more buses, how can I use and optimize my network design to decrease the cost of the whole vehicle? Data coherency. We've seen that. We have one source of truth, right? This was the theme for the MBSE flow. How we can start from the same source to feed signal, to feed networks, to feed EDS, and to feed software, making sure that we all took or we all use the same source of data. And again, we're not using documentation. We're using model that we can interrogate and make sure that it is a coherent and consistent data, which is gonna affect directly your quality, right? So data coherency has a one-to-one mapping with improvement of the quality. And finally here, the automation, right? So automation is a big factor, as we've mentioned earlier. As the complexity are growing, that we need automation. This is what we provided here with generative flow to be able to generate frame packing and generate timing reports early on before even thinking about physical testing. And some advanced topics that you cannot handle using the current tools or the old way to do network design that we've seen OEMs, very big OEMs, that are using Excel sheets to handle their network design, they will fail, big fail, to handle those topics. They are not able today to take this model that has been in the market for, or in their vehicles for years, to their suppliers for the ECU. They cannot. They cannot provide an ECU, an AutoSAR extract. They cannot handle today's service-oriented architecture, which is the most big thing for the future, right? They cannot do Ethernet or Ethernet-based design using the same old ways. So how they handle partial networking and network management using some documentation. So all those advanced topics cannot be handled the same old way that we used to use to handle LAN and CAN, right? This is why we are in a disruptive mood. So those new concepts would need a quite new ways to do our network design, and this is the main value for having a tool that understands the model and understand the past and are ready for the future. Those are the tools that will really help you to cover or to overcome the issue that we discussed in the first slide, right? When we have the complexity that is being growing as we go.